Okay, hi everybody and welcome to this webinar on model-driven design of multi-cloud application with a priori QoS guarantees. I'm Michele Ciavotta, a postdoc at Politecnico di Milano, and I'm just one of the two speakers for this webinar. The other one is Marco Almeida from Soft Team. We decided to split this seminar in two parts. In the first part, Marco will show you the design time application for modeling functional and non-functional properties of a cloud application. While in the second part, I will show you the Politecnico di Milano tool for QoS assessment and optimization. Let's start this webinar talking about about the motivation that are behind what is the Moda Cloud environment, and I will tell you what is Moda Cloud in a few slides, in a few minutes. What are the motivation? First, we saw that the cloud in the last years that the cloud in the last year changed the way in which the software, the application is designed and developed. According to, above all, the ability to provisioning pay-per-use resources in an almost infinite way. And this is changed a lot in the way in which we plan the capacity of our for example, of our data center. In fact, usually before the rise of the cloud, we used to overestimate the need, the requirements for a certain facility, because we decided to deal with usage peak. Okay, but peaks are rare and relatively short, and this made to our data centers to be underused. In fact, only on average, only the 10-50% of the capacity is used on average. And this means large cost for, above all, electricity and cooling. And also for this to deal with a very usually an average low demand. With cloud, on the other side, we can exploit elasticity and only allocate resources and pay for them when they are required. Another thing, with virtualization, also, that is at the base of cloud revolution, it was quite difficult to set up the hardware for the application. We have to configure operating system, network, storage, and so on. And this for each tier for each tiers of our application. While now, with the availability of virtual machine, we can set up each tier once and then clone the machine and scale them. Okay, but it's not everything. Everything is a good thing, because with cloud we now have new issues that were inconceivable before. First of all, heterogeneity. That means that when we decide to design and realize an application for cloud, it means that we almost marry our cloud provider. And this is it can be a huge problem, because if at some point he decided to change his policy and we do not agree with them, we have to spend a lot of money to redesign our application and redeploy it on a different cloud. Also, and this is a problem because there is a lack of interoperability among different clouds. But it's not just like that. Also, cloud performance can vary at any point in time, and this especially difficult to deal with when we have to build an application that is stable and can handle several thousand of users at the same time. And related to the previous problem, there is also the problem of unavailability that is important even when cloud providers advertise 99.9% of uptime. So almost 3 years ago, we started with this big European project named Moda Clouds, and we have, how you can see, several partners all around Europe. Among them, there is Politecnico di Milano and Softeam. The aim of this project, is to realize a design time and a runtime environment. In the design time, both of them are based on the model-driven development approach. And in the same time, we realized we implemented an integrated development environment, an IDE, called Creator for Cloud, and a set of other tools. And at the runtime, we designed a platform with several interesting things like monitoring platform, self-adaptation, reasoning tools, and automatic development tools. But what is important in this project is Soul that want to generate multi-cloud application, guaranteeing both a design time from scratch, the quality of service. There are many. I mean, if only we consider the design time part of our project, we can see that there are many tools and many stakeholders involved. In this presentation, however, we will consider only the two white boxes here, which refers to Creator for Cloud and Space for Cloud. Creator for Cloud, as I told you, is a functional and non-functional modeling environment, while Space for Clouds received in input the models generated by Creator for Clouds and returns a prediction on the quality of service and performance of the application, even before the application has been physically implemented. In this slide that will provide you at the end of the talk, you can find some useful links for downloading the tools. As you can see, Creator for Clouds can be downloaded directly from Modelio platform, from forge.modelio.org, while Space for Cloud is more a set of tools, and you have to download Eclipse, Palladio, the Space for Cloud plugin, and Line. That is our solver. Here we are. Those are our photos. It's Michele and Marcos. I can assure you that we are more handsome in person. Marcos will talk to you about model-driven multi-cloud application design using Creator for Cloud, and also about the case study of this presentation. While later, I will talk to you about methods and tools for model-driven development and design time exploration. Marcos, if you're there, I can switch. You can switch the presentation.
Yes, I think people can see my screen now. So let me just go on. So hi everybody, my name is Marcos Almeida. I'm a research engineering from a soft team. That's a French services company, and as part of our activities, we have a product that's called Modelio. It's a modeling tool. And in the Model Clouds project, we have a double role. So we are at the same time tool providers. So we are extending Modelio with the concepts that are needed to design these multi-cloud applications. And we are case study providers, so we have a case study in which we are basically providing Modelio as a service on multi-clouds. So that's why we are going to use this case study as an example for this webinar, and that's why I'm going to present the case study. So let me just, this is the case, one of the case studies of the Model Clouds project. So why is it interesting? Because it's a real industrial application where we need to have multiple clouds, and we need to have some quality of service hints on what's the quality and the cost of the application before before deploying it. As I told you before, so we have a product that's called Modelio, so it's based on Eclipse. So we're going to find all the common interface concepts you have in Eclipse, views, and but that instead of editing code, you're editing models here in Modelio. And the idea is that it's a UML editor, but we also provide many extensions of UML to target specific domains. So we have extensions to target SysML, that's embedded systems. So we have extensions to target Martyr, that's real-time systems, UTP, that's modeling tests of applications, and many others. So we have modeling for Java code, for database, and lots of things. And we have services that are built on top of this of this model. So we can generate code, we can perform model transformations, we can generate documentation from models, and we can work in teams, in groups. And it's open source. So I invite you to visit us after this webinar, take a look at our website and what we can propose there. But the most important point here is that we in the last years we saw that the projects are getting more complex. We support many different domains, so maybe we start getting projects where people mix different domains, different models, and they need to work in teams. And what we wanted to do is say, okay, let's change the paradigm, go from this desktop paradigm where you just buy one license, download it, and use it in your desktop, to go to the cloud paradigm where you can have some cloud-based management of resources, and it's easy to work in the teams and to make things scale. So that's why we came to the idea of constellation. So the idea is having, okay, let's have Modelio as a service on the cloud, and so we can, instead of having just SVN repositories in a single computer, you can have some online interface where people can say, okay, I need these and these resources. I want to create a new project. I want to do this kind of services, and they as customers, they don't need to care about where they're going to deploy things, where they're going to provision this service. So that's the idea behind Constellation, and that's the challenge here. So how to create the architecture of this service, and we had Model Clouds, and the things we're going to present in this webinar help us to get to this architecture. So and then that's a good think that in the last 6 months we started selling it. So the modules we present here are really part of this, of an industrial application. I have a demo on Constellation. Let me first. I'm going to show Modelio. Just you understand what's it about. So it's a modeling tool. So just like any other modeling tool. So it's UML. I think most people heard about UML once in their lives. So we have classes and that are boxes, and then you can connect these classes. You can define attributes. You can define many things about these elements. But and the important thing and the reason why people buy these kinds of tools is that it's not just a drawing, but you can take this drawing and use it as input of computation. So you can write some model transformations. You can so in Modelio you have a system of modules that are extensions, so people can write code that does some transformations and some computation on these elements. So we use it to generate code, to generate documentation, and many other things. And just to show quickly Constellation. So the idea is that it's not just something you have in your desktop, but it's also something you, as a customer, you buy. You have it provisioned either in a public cloud that you don't need to care about, or in a private cloud that you have inside of your company, and then you can manage the projects you have, the models that these projects are going to share, the libraries that are pieces of models that these projects are going to share, and modules and all these things. So you can manage these things, and then you manage them as a service, so you don't need to care about where and how these things are deployed. But then you have some kind of management support for this kind of services. Let me go back to the presentation. Okay. So what we need here is not just a cloud application. So what we could have done is just write the application and then have it in one cloud provider and be happy with that. But the problem is that, as Michael said, when you write your application, as soon as you finish it, you're trapped into one cloud provider. So we wanted to be independent from the vendor, so we could support more customers. Like some customers have already some cloud accounts, or they have already some internal private clouds, and we would like to support these things easily. We want it to be cost effective, so we are selling the usage of resources, so we need to know how much things cost before deploying them. So the kind of tools we're going to present in this webinar are very important for that, to make this analysis and helping us to get figures before spending money in deploying things. And then automation, that's something that we're not going to show in this webinar, but we have lots of support for automating the deployment and management of cloud application in the Model Clouds project. So it's over with the case study. Now I'm going to show what are the principles behind the modeling support we provide. So, okay. So the idea is that we provide what we call a model-driven engineering approach. So just to make a comparison with the traditional engineering, that is that in the traditional way of doing these things, that we have lots of artifacts that are like code or models that people in the project are going to use at the same time. Maybe they have some kind of versioning tools that are going to mediate this use, but that is that they are going to simply use them separately and make the best they can to make things consistent. When you are in a model-driven engineering, project, the idea is to have a single model that's that concentrates all the everything you know about the project, and then the people are going to work in this model. So maybe the model is composed by different domain-specific languages, but it's still a single model that you can verify, that you can check, that you can use to generate the artifacts that they need in the traditional engineering. And that's what Creator for Cloud does. So it is that you have a single model that you can work on, and then Creator for Cloud is going to mediate the use of other tools and make the interface between all these tools you need. Wait. Okay. So what are the requirements of what we wanted to do in Model Cloud? So we wanted the first challenge was the heterogeneity between cloud providers. So we need an abstraction to make sure that people can have a single model with abstract concepts, and then using these concepts, they can describe what they want without needing to care about the difference between the cloud providers. Then the second point is, okay, the providers are heterogeneous, and even when they promise triple line availability, sometimes problems happen, and you have hours or days of unavailability, and you need something to manage these resources automatically. And then finally, we need to no approach is going to take care of all the details in a single abstract model. So we need to have some way to have developers say, okay, I know in this specific case for this specific provider, I need to do things differently, and we need to have some runtime support for adapting the application at runtime. Again, in this webinar, we're not going to focus on the runtime things, only on the design time things. So I think I'm running out of time, but the idea is saying that, okay, different cloud providers, they support very different sets of concepts, and the idea is having a common set of abstraction that we can use to describe the application, and to separate what's dependent on the providers and what's independent on the providers. And then that's the thing we really are looking for in these projects, and that's the thing we support with Creator for Clouds. The approach of model clouds is basing the modeling in 3 abstraction levels. So the idea is saying that you start as a developer by describing an application by means of the model, what we call the cloud computation independent model, saying, okay, imagine if my application is not a cloud application, it's just an application. Forget about the cloud. What do I need? What are the services I'm going to provide? How do these services connect? What are the interfaces? What are the resource demands? And what are the QoS constraints? Once you have an idea of that, you can start thinking, okay, I know what are the services I need. I know the kinds of providers that there are in the world. So even if I didn't choose a specific provider yet, what are the kinds of services I'm going to implement myself, and what are the kinds of services I'm going to reuse from some provider? How can I deploy these things, even if I don't know exactly what's the provider? And then the final level, we have models that say, okay, this is the kind of provider I'm going to use. This is how to connect to this provider, and so on. This way, we can separate the things that are completely independent from the cloud from the things that are really dependent from a specific cloud provider. And then I'm not going to say that you're not locked to one provider, but then you know exactly which part of the project is locked to that provider, and which part of the project you need to rewrite or to reuse or do something more specific to make sure it works in another cloud provider. And then it helps you in separating these things and reduces the cost of development because you think about these things in advance. I think I'm going to show the model in Creator for Clouds. I think you can see my screen. So the idea, let me show here, is that a model in Creator for Clouds, a model of an application is divided into the legacy model. So in Modelio, we have lots of tools to importing existing code or database or many different things in the form of models that you can use as part of your model of your application. But then out of the use case of importing legacy things, you have three models. You have the cloud independent model, the cloud provider independent but cloud-based model, and then you have the cloud provider specific model. As I told you, in the cloud independent model, you just describe the services you need in your application, and then for each service, you specify what are the constraints that you need to meet in this service, what are the interfaces, and for the interfaces, for example, what are the resource demands for each operation in the interface. So, for example, you can have a matrix here saying that, okay, I have two constraints on this HTTP agent service, and then that are about the average, and then the 85 percentile or the execution time of an operation. So you have all this kind of information in the model, but it's not only a description of the services, but you also have a description of the connection between the services. So you can say that's the architecture of Constellation that I showed you before. So it is that you have an administration server that's going to be this web interface I showed you, with a database that's going to keep all this information about users and projects and so on. And then we have an agent manager that's going to keep track of agents and resources. So the idea is that when you, for example, when you create a project and you create a model, this model needs to be stored in a resource on the cloud somewhere. So the agent manager is going to take care of choosing where this model is going to be stored. And you're going to have either an SVN agent or HTTP agent to store the model. So an SVN agent is for read-write models, so models people are going to work collaboratively on, and HTTP agents for models that are read-only, so people are just going to download it and use it as a reference and connect it to other parts of the model, but not change it. So I hope it's clear. The architecture is simple, but it's going to be important for understanding the rest of the webinar. So again, you have this central server, and then you have agents that provide modeling services on the cloud. That's the view of the application independently on the cloud, independently on the cloud provider. We have lots of other information here, so I'm going to show it quickly because I think I'm running really out of time, but we have models on the behavior of the application. So for example, when someone tries to read the project description, the administration server is going to access the database to get information, for example. So we have a model of how these components interact. We have models of how users interact with the application. So I'm not going to explain it in the details, but the idea is that we have a model of how people use the application throughout the day. So what are the operations they call, what's the order, the scenarios they they use to call these operations, what are the probability distribution of each scenario, and so on. So have all this information. So have, like here, have a model of how many people use the application throughout the day, how long they take between different actions. And so using these models, that's what we're going to see in the second part of the presentation. We can have a very good analysis on how the application is going to behave and how you can improve its deployment. I think it's enough for the cloud, the CCIM model. Just showing quickly at the CPIM model. So you notice that I didn't talk about deployment. So at the CPIM model, you start talking about these things. So you have a model of the cloud nodes you need, and a model of the features, the properties. You have a model of the applications or services that you can reuse from cloud providers, and a model of the resources that are things you can deploy. So you have common, in here you need to say, okay, how to download this resource, how to install, how to configure, start, stop, upload, and then the runtime components of model clouds can do these things automatically, given the commands we provided here. And and then we have this instance level model that says, okay, how these components going to be deployed on cloud nodes, and how do they connect. So we see that the administration server and the database and the agent manager are usually deploying the single node, and then you have SDN agent and HTTP agents that are usually in separate nodes, and you have all this information here. So you have connection between the QoS constraints and nodes saying that, okay, this agent is not replicable, so you can't have a copy of an SDN agent because people work on a single agent, single SDN repository. You can't scale it. And finally, just to give an idea of what's in the CPSM, what's the difference? What's the added information in the CPSM? You have cloud accounts. So say, okay, I have an account in Amazon EC2. This is my credential file with my keys, and these are the other properties we need to initialize the connection with Amazon. So we have all your cloud accounts, and then you can in your CPSA model, you can have deployment models that are just, hey, I have these components, these kind of cloud nodes, and these are the specific resource we need in cloud providers to deploy it. So for example, the admin server, I want to deploy in the Spot small instance, and the SVN server, I want to deploy in a FlexiScale 1 GB CPU. Notice that here we are referring to resources provided by, by cloud providers. So we can see that in Creator for Clouds, we have here a set of what we call the resource model. So it's a model of the cloud providers that we support, and for each cloud provider, we have the set of cloud resources that are made available to this by this cloud provider. So making an application multi-cloud, so it's just a matter of, it's a drag and drop. You just say, okay, this node needs to be in a on-demand micro instance from EC2 from Amazon. So you just put it in your model and say, okay, this guy is going to be deployed here, for example. And then that's how we get the multi-cloud model of your application, because it's really independent on the rest of the architecture of your application. I think that's the most important parts of the model. I could talk more and show more things, but I think we can go on with the presentation. Let me just go back to my PowerPoint. Okay, I think that's all I had to show for now. I think there are no questions, so I think we can go on with the rest of the presentation with Michele. Okay.
Okay, thank you, Marcos. I think we can go on with the presentation. And in this second part of the webinar, I will talk about model-driven performance assessment of cloud application, which is a problem of software performance engineering. And in this field, we devise models and methods for performance prediction. This means that for having the model of the application, we can derive a prediction on the application response time or the response time of each functionality in the application, and or the resource utilization of the or the throughput linked or related to the application. Uh, but why we want to do this? Which is the goal? The fact is that if we know exactly, or if we have an idea or of what is the resource demand of a certain application, we can plan the capacity of our cluster. That means on the hardware that we want to buy and install to run our application, or we can have an idea on how much it will cost to run the application on the cloud, and also decide or plan a minimum cost resource provisioning. Uh, this can be this has like two major decision point. I mean, the deployment can be decided at the same time if we have a rough estimation of the workload, or at runtime with a self-adaptation mechanism. But what is important for now is to have an idea of the performance of the application. And the model-driven quality assurance has been born to bridge the gap between software development and software performance engineering. That usually is very loose. From one side, we have all the models that Marcos just show you, and from the other side, we have different kind of models that are used by QoS engineers to predict, to assess some performance indexes. But the model-driven quality assurance want to merge these two levels, fostering collaboration. How? With an automatic, like proposing automatic transformation from one model to the other, and this can be done by a set of annotation. That means that we can annotate the UML model with requirements of a single functionality, and use these requirements to create a performance model and then solve it in order to have the information that we want. So two elements are important. The one is the annotation. The second one is the model-to-model transformation, and must be automated, of course, because usually software engineers don't have the skills to create performance model. We have several performance models. I've just listed five types here, like queuing models, layered queuing models, Markov chains, stochastic Petri nets, stochastic process algebras, and so on. And they are like complicated, let's say complicated models. that must be created starting from UML model. This is the model cloud approach that we devised. We saw how in Creator for Cloud we can model the application. So we have the application model. Then this model must be fed in input to Space for Cloud. That is like the tool where Politecnico di Milano is more involved in the development. But this tool is based on another tool that is called Palladio. So first of all, Creator for Clouds transform models into Palladio component models. Then that are a special language. Okay, but the set of information remain unchanged. So we have the same information but in different format. Then we inside Space for Cloud we transform during the optimization and assessment part. We transform the Palladio component model in layered queuing networks. And since we want to analyze the trend of a typical day, we generate for each hour a particular model. So we have to solve 24 models for each possible deployment. And how we solve it? We solve it using LQN solver. And Space for Cloud has been designed in order to use several solver, and in particular Line that is being built within Moda Cloud project, or LQNS that is a different solver. Line, but Line is special because it's the only one that is able to return as response time distribution for a certain functionality, and is fast if compared to other solvers. Standard analytical solvers also, like Line. The Line is based on liquid methods. While standard solvers only can give us approximate percentiles and mean metrics. Also, we could use in theory simulation tools that are computationally more expensive. Okay, I will now start to get into the tools that we have developed. Okay, this tool in the workflow of Moda Cloud IDE is here. Is the QoS modeling and analysis tool. We will generate an optimized solution. This means that we try to optimize the development of an application, of a multi-cloud application. This development with this configuration can be used to deploy the application on several clouds through Moda Cloud ML, or through Cloud ML and Moda Runtime, that are other two tools of Moda Cloud's toolset. Okay, what is the goal of Space for Cloud? He wants to identify minimum cost configuration. That means a set of cloud providers, a set of virtual machine type, and a load distribution along the day. That minimize, the configuration that minimize the cost, but respecting or fulfilling some QoS or architectural constraints. But what we have to face? We have to face the fact that the solution space is huge. Why? Because the offer of cloud providers is huge. They have several, only for IaaS providers, they have tens of different virtual machine types, for example, and each one with different, having different performances. So if you want to we want to seek for the optimal solution, we need actually a lot of time. But also cost estimation is difficult because we have several pricing models, and these models have several cost metrics, and these metrics can depend on different indexes like time or number of bytes sent, for example. So we had to first devise a proper model for cost and then a proper model for performance. And in this scenario, we propose our solution that is, as I told you, space for clouds. That we want to propose as a support tool for QoS engineer. This is the architecture of Space for Cloud. We have like in input the models from Creator for Cloud or Modelli, and within our tool we have two main components: an initial solution builder and a Taboo search optimizer. The initial solution builder is, let's go a bit on. The initial solutions builder identifies an initial configuration of the system on a time horizon of 24 hours. And the idea is to meet QoS constraint and minimize cost. From the model generated by Creator for Cloud, we create a mixed integer linear programming model that is based on simplifications. And for example, it does not consider percentiles and is based on MG1 queues. But QoS and architectural constraints are not relaxed. At least not all QoS constraints are relaxed. This means that if we decided that for a certain component we need at least two cores, a machine with at least two cores, or at least 2 gigabytes of RAM, this model will we will consider this constraint as a hard constraint. So if we will find a feasible solution, this solution will consider those constraints. As far as the Taboo search or the Taboo search engine is concerned, we have in simply put, we have an engine that perform a search on a neighborhood, performing small moves. This means that we change the solution in some part, and we evaluate the solution again. If the new solution is better than the previous one, is considered as the center of a new neighborhood. In a Taboo search engine, we have also a memory structure that impedes us to make the same move again. This means that in this way we will not cycle in the solution space. We also have to make some disruptive move because from time to time we have to change the type of VM. So each time we try to save the best solution found so far. But I use this image to try to explain this better. We can, having a certain deployment, we can scale in or scale out some tier. But every time we change the VM type, the number of machines of that tier has to be recalculated from the beginning. Here we define an hierarchy of moves. In particular, we can scale in and scale out. We rebalance the load among several clouds, and we change the VM type on each cloud separately. I can use this image to explain this in a graphical way. We have in input the enriched Palladio models with description of constraints and description of the workload. Then a set of candidate cloud providers, in this case Amazon, Google, and Azure. But we decided that we want to use only two of them, for example. And this input is crunched by the optimization engine. And first of all, an initial solution based on MILP is generated. And then this solution is used as a starting solution for the Taboo search engine. At the end, during this process, we will use performance engine like Line, LQNS, or Simcom to evaluate the solution that are continuously generated. And at the end, we have a complete, let's say, we say a complete solution, a complete configuration of two, in this case, two providers, Amazon and Azure, with the allocation, all the allocation profile. That means the number of virtual machine for each hour, and the type of virtual machine associated to each tier. So to each tier. Okay. So let's go back to our case study. Okay, so in collaboration with Marcos, we did the follow. We tried to, he realized a model of constellation server for us. And we used Space4Cloud to analyze the performance of this system according to a growing workload. And we find out that there was I wouldn't call it a mistake in the architecture, but there was a so-called bottleneck. So there was a point of the architecture that could not scale and that limited the number of users that can be logged in and work on Constellation server at the same time. So we decided to study these three possible options. I mean, if we can find a bottleneck and how the bottleneck affects the system performance, how the system change, or yes, in terms of types and number of virtual machines by varying the number of users, and how do the costs vary accordingly. Okay, we have first to decide which is the input workload, and we took this. We decided to use this shape because it came from a real log from a large Italian website, and it's quite clear. I mean, in the central hours of the day, let's say just before lunch and just after lunch, is the moment where people probably will use this software more. And so we have the so-called bimodal distribution of users. And those are the constraints that we decided to set. We have several components, but in particular we have a commit and an update component. And we set the average response time of the commit component to be less than 60 seconds, the 85th percentile of the response time to be less than 5 minutes, the update less than 50 seconds, and the 85th percentile to be less than 30 seconds. But we also have two architectural constraints. In the first one, we say that the admin server and the SVN agent, have mean and max replica equal to 1. This means that they cannot scale. Okay, now I will try to do something. I hope it is going to work. I have a virtual machine here with installed our tool. It is Space4Cloud. It is Eclipse plugin. This one. We can just to be. I mean, in this plugin, I can change the possibility to assess from assessing the performance of a certain application to optimize it. But I cannot show you the optimization here because it's a quite long process. Depending on the kind of machine, it can last from some minutes to several minutes, even half an hour. So we decided to show you the performance of Constellation server. The Constellation server under 200, sorry, the SVN, yes, Constellation SVN version under 250 users at peak. Okay, so we can start the analysis. Here we can see that if you could read this as I can, you can see that we first generate a model, a mathematical model, then solve it, and then connect to line server in order to evaluate performance of the model. It should take some seconds. I will explore the situation to go on or not. Okay, I want just to tell you that all these model, used model, allocation model, repository model, system model, contain the exact same information that you saw before in Creator for Cloud. Okay, this is the result of our assessment. Okay, let's see. We can see that the almost all the for 250 users, almost all the requirements are fulfilled, but one. The constraint on the SVN agent. Okay, this one. What is happening? Since we look at the number of machines, we have that during the whole period we have one or two virtual machine. But since the SVN agent cannot scale, this is the blue line. Actually, you can see that it is assigned to only one machine always during the 24 hours, and that the utilization reached 100% in two moments, corresponding to the 11th hour and to the 16th hour. Here we can see that the constraints on the average response time is not met. And I show you an assessment, but the solution that we are considering now is a solution obtained after a run of optimization. This means that Space for Cloud wasn't able to find a suitable solution for 250 users. Why? Actually, this means that there is bottleneck in the system. And let's analyze the situation more carefully. With 50 peak users, we have that all the system can be deployed on extra small VMs, and the SVN agent on a medium VM, because it is the component that made more work. When the peak is from 100 and 150 users, the SVN agent must be located on an extra large VM, while the other components, they have a low workload, a low load, and they can still be deployed on extra small VMs. But at 200 user peak, we have to scale the HTTP agent to using two extra small VM at peaks. We could use a larger machine, but this would lead to a higher cost. And this is the case that I showed you before. We have the 250 users at peak. We have to consider, even considering 5 extra small HTTP agent machines at peaks and an extra large virtual machine for the SVA agent, the solution obtained is not feasible. Okay, and here we have the models the response time model associated to the update and commit functionality of Constellation. And we can see that when we grew up to 300 and something users, the response time of update model goes goes up to the threshold, while for the commit model, this the number of users like go down to 250. Okay, we have here an alternative architecture that with the help of Marcos we could devise in order to avoid this situation. I would ask Marcos in this case to help me to describe this image. Marcos, could you tell us which are the major changes in it?
Yes, as I explained before, the idea is that the base architecture was based on SVN and HTTP models. So the point is, when people are working in one project, they need to connect at the same time to one SVN server, and then this server becomes the bottleneck because you can't scale it, you can't duplicate it, you can't do anything with one SVN server. And since the application, the modeling is a read intensive application, so that means people spend much more time reading than writing to a model. And this kind of application is really, as I wrote here, high tolerant to eventual consistency. That means that if we have different people writing in different parts of the model, we can wait a certain amount of time until all the models of all participants are consistent. We don't really need a temporary inconsistency is not a problem. So the idea of this new architecture was separating the reads and writes. So the idea is that we have a conference agent, have an arrow here, right? So it provides the right services, so we can open a project and we can commit to modify something in the model, and then you have replicas that are read only. So and that users use it just to read the modifications. So every time someone writes in the main in the conference agent, it's going to send this information to all the replicas, and then they get this information, then they send it to Modelio clients. So that's the basic difference between both architectures. So the idea is that since reads and writes happen in different nodes, so even if some of the reading nodes become a bottleneck because people are reading at the same time, we can split it into two copies and then to make it scale.
Exactly. Now I will try to show you again a new live demo in which we will assess the okay, this is the old one. We are going to assess the performance of the new model, the one that has been called conference. We with the help of Marcos devised this new architecture, made the new models, and we optimize it, and we show now the results for the optimization. In this case, I only assess it. We consider here the case of 500 users, only to demonstrate you that this new architecture can scale beyond the limits of the previous one. Again, we have to wait some seconds. During this time, I will show you which are the constraints that we are considering now. Now we have the first 4 lines are the same constraints considered for constellation. Since we have now a component for a partial update, we added 2 more constraints on it, where on the average response time and on the 85th percentile. Again, we have 2 components that cannot scale. Instead of the SVN agent, we have the conference agent now. Okay, let's see. Okay, we have here our models evaluated. Let me simplify a bit this. Okay, remember the. Okay, now we have like deployment on 3 tiers, the green, red, and blue one. And we can see that if we don't consider the blue one, that is the one related to the commit of the conference agent, all the other tiers can scale. Utilization reach the 100% only for the read-only conference replica, but it can scale, so we can meet our. Usually, in this case, we can meet the constraints. In fact, as we can see here, the conference agent commit is 30 seconds, and since the blue line is the one that we were concerned before, is under this threshold, we are fine. This means that in this way the application can scale beyond the limit of the previous one. But it's not all. I will show you in a second. Look, this is the daily cost trends for several peaks values. And we can see that in this case, we are always able to find a solution that has a smaller cost with respect to the previous one. Why? Because we now can scale and use cheaper machine than buy or look for larger and more expensive machines. Yeah, again, we have one virtual machine. I mean, one tier more. Conference agent has to be medium. The other one start scale at 200, at 300, from 300 to 400 peak users, and we can see how the conference agent, that's the one that cannot scale, is located now on a medium and not on a less extra large VM. That's important. Those are the updated commit models for the new and from the old architecture. We can see now that how the conference response time is always below the threshold that we imposed. Okay, we reached the end of this webinar. Those are like our future work. I mean, we want finish to validate our solution with industry case studies, in particular with keep working with Marcos. Okay, well then we will have to finish the tool for filling the gap between design time and run times, because all we have done now is based on prediction of the resource demand for a certain component. But when we deploy the component, then we can calculate real demand and then update the models at this design time in order to find a more suitable and hopefully cheaper solution. And also from our side, at least at Polytechnic in Milano, we have to finish to to complete the adaptation at runtime adaptation measured that are based on the model that I have just shown you. Okay, I think we can. I mean, it's all from our side. If you have question, please ask. We are here for you.
Questions. Hi. Hello.
Hi.
Can you hear me? Hi.
Yes,
I have a question for you.
for me.
I
Okay.
Yeah, yes. My question is, you just mentioned the QoS specification, and I'm wondering what kind of QoS, and you also mentioned uh, the cloud computation independent models in the QoS specification will be included in the model, and what kind of QoS attributes are included? I think that maybe this kind of QoS attributes must be provided by the cloud provider. What if there are some QoS requirements not included in the SLA of cloud providers?
Okay. Yeah, I mean, let's start with the kind of QoS metrics that we can consider. If I'm not wrong, but please, Marcos, correct me if I am. We can consider average values of utilization and response time. And but also percentile on the response time for a certain for a certain functionality. And yes, it's true that we can define this QoS requirement at cloud independent level, and since and I mean and at the moment in this, as far as this presentation is concerned, we don't need the cloud providers to expose APIs for having such information. Because we are just predicting the behavior of the application. But I can tell you that in our part of Moda Cloud's platform, we realized we implemented a monitoring platform that is cloud independent and is able to provide us with the all these metrics. Actually, with many other metrics too. I don't know if I answered you answer to your question.
Okay, another question. Okay, thank you
Yes.
for your answer. And another question is about the prediction, performance prediction part. You just showed us a graph on the on the user click daily on a website, and
Mhm.
maybe it's based on the assumption that every day the workflows are almost the same, so you can use the model to predict the workloads. However, what if for in our real life, especially in some holidays, maybe more the behavior of users there will be different. So the prediction maybe based on this model is not correct for these holidays or something.
Yes, I understand very well your question. It is also very important. But what we have done is to generate at higher level a set of a set of different scenarios, and we can consider several different shapes according to different day. For example, if you are selling stuff, I mean, if our website, for example, is eBay, and we know that the shape of the workload will be much higher during holidays. Uh, That's why in that case we have to do two scenarios. One for the normal, let's say normal days, and another one for peak days. But that is as only I mean, at the same time, this does not make is not that important as you can imagine, because usually, even if we consider the daily trend, we what is important for us usually is the peak value. So we want to, I mean, we just want to answer the QoS engineer question about my system will be responsive if 1,000 people will log in, will use it. It will be responsive if 10,000 users will log in, and so on. However, thank you your question, because it means that you really understood what I was saying before. Any other questions?
Wait, I just want to complement your answer. Wait, just to show, I didn't talk about that in the details, but the idea is that in the model you have you can create several what we call usage models. So each one has this what we call here workload specification. That is the shape of how people use your application, and then you can have different ones for different situations. So you can have one for holidays, one for normal weekdays, and here in this use case we just tested one with the SVN agent and one with this new architecture based on the conference agent. But then we can explore other configurations with the tooling we have.
So at the end, can we get your slides?
Yes, of course. I have your email address, and I will send you just a little after this webinar ends. Okay, if there are no other questions, I will just thank you for coming. Hope you enjoyed the webinar. Bye to all.
Bye bye.